Hello and welcome to our CAN and automation webinar on the topic CAN and cybersecurity. This is a 1-hour webinar. It is a short update to what I have talked about a year ago on our webinar on CAN and cybersecurity. To start with the webinar, I want to start with a short definition of cybersecurity. It's not the latest update, but it is taken from Wikipedia. And what is cybersecurity about? Cybersecurity is computer security or cybersecurity or information technology security, IT security, is the protection of computer systems and networks from information disclosure, theft of, or damage to their hardware, software, or electronic data, as well as from the disruption or misdirection of the services they provide. Of course, these days, it's not anymore just IT or information technology. It's also for, the definition also applies for the embedded world and other automation systems, or sometimes also called as OT, and in this case, OT security. As this is a short webinar on security, I will shortly introduce myself, and if you don't know, CiA as well. My name is Schumann. I'm right now with CAN and automation for over 25 years now. I participated over time and still participate in different standardization groups on national and international level. I participated in the standardization of different application layer and application definitions within CAN and automation, meaning lift applications, specialized special car equipment, municipal vehicles, and things like that. Over the years, I moved a little bit away from that and specialized more in basic technologies required for the communication within those networks, specifically regarding safety or functional safety and security, cybersecurity. What is CAN and automation? CAN and automation is a non-profit organization founded in 1992 with the objective to bring CAN technology forward. Just to remind you, CAN was developed beginning mid-1980s, so it was first published 1980 as at a SAE conference. And it was in the very beginning of the using of the CAN technology in the different application fields. And so CAN and automation was founded to provide and enable the use of CAN-based technology in different application fields. Anything you can think of. I used to say we do anything except bikes, but over the years and in the last years it's shown that CAN is now also in bikes and pedelecs and e-bikes and things like that. You see, we have CAN almost every day in any environment. CAN, it's the organization itself grew over the years. We are right now more than 750 members worldwide. Mainly in Europe, but we are working worldwide and serve to our members worldwide. As I said, we were founded in the beginning of 1992. We organized a different joint booth at different fairs, international fairs, so you can visit us at the upcoming Embedded World here in Nuremberg, if you like. That will be our first exhibition this year, and I assume our last exhibition this year at the end will then be the SPS. And over the years, throughout the year, you will see can meet us also in many different other exhibition and fairs and conferences. We also organize the International CAN conference every other year to make them update to the latest technologies on what's happening in CAN. One of the big things at our International CAN conferences, of course, is the presentation of the development of CAN, which was in 2012 the presentation of CAN-FD, and in 2018 the first, in 2019 the presentation of CAN-XL. Our main topic, of course, the CAN specifications, and our support of is around those specifications in terms of information about those specifications, like in our newsletters, updates in dedicated work, like in the International CAN conference, and information with seminars like these short webinars today, or dedicated seminars we organize, and also provide in-house seminars if you like to participate. From our technical point of view, we are organized in different technical groups, observed by the technical committee. So we have technical groups for the CAN Open specifics, definition for CAN Open FD, and for our dedicated device and application profiles, we have a profiles dedicated group. And we have dedicated interest groups for the lower layers, namely for CAN-XL, CAN-FD, and also a dedicated group for safety and security. As I said, you are happily invited. We have organized our International CAN conference. The next one will take place in Baden-Baden in mid-May. Where we will have there the latest updates to CAN-XL, and also some updates on security, safety, and other important topics. If you like to stay up informed, we provide the CAN newsletter magazine. We have information on our website. We provide different email services. So if you would like to stay updated, yeah, just email us and you can be subscribed to any of those information sources. So coming to the main topic, to the topic of security, cybersecurity, we have, I would say, three main international standards on the topic of security, cybersecurity. It's the ISO IEC 27001, which is coming mainly from the IT industry. It's defining security techniques, information security management. We have for industrial control the ISO IEC 62443 series. It is dedicated for industrial communication networks, network and system security. And we have for the automotive environment the ISO SAE 21434, which is intended, for automotive, for road vehicles, and the cybersecurity engineering thereof. We have also different legislations in different countries, like here in Europe, coming up, the cybersecurity directive, which will be released in a few years, and we have the upcoming cybersecurity requirements for automotive. Most of those directives and rules and regulations, of course, reference some of those standards. But what is required according to those different standards? And if you look in the organization of the standards, they are organized, and of course, their requirements regarding that is mostly the same. So if you look at the IEC standard for industrial control, we see Part 1 defines the general terminology, the concepts and models. We have the definition in Part 2 of the general system of the industrial automation and control system from the system point of view. So establishing the system. We have in Part 3 the operation of the systems, and in Part 4 there comes the specific security requirements. And then each main part is then also being developed further down in the subparts. So we see we have first the policies, the system, and then going down to the component definitions. But what is been really in there? What is the main part of the definitions? And the main part is, if you think about security, we first need to think about, or need to identify basically what are our important assets in the system. Is it credentials? Is it firmware? Is it certain data? Anything. And then if we identify such assets, we need to identify the according threat models. So who is who's trying to access those assets, which is not allowed to access those assets? What are the ways to get access to those assets? And only when I make my work in the first 2 points, then I can start to define the protective measures around. Of course, I have to verify those protective measures if that works, and I have to reiterate over the whole lifetime of the system over and over again, and have to adjust my protective measures and basically going into an update cycle. So that means what's being defined is all the complete parts of the whole life cycle of the system. And we have to improve our system. And what we see in cybersecurity, we have a system view first, and then we can go down to the detailed components, to the devices, and look on what is being required there. Also important is the decommissioning part of our system. Also that needs to be considered, especially if we think about, security is about encryption, and we do encrypt and everything is fine, and things, you need to think about, if we do encryption, we need keys. So what happens with our keys during decommissioning? They are still present in the devices. What is if someone is able to read them out and compromise with that kind of information other active running systems? So you see, security is not just a pure thing. I do some encryption. How do I implement encryption and things like that? I have to think the whole system. What are the important assets to protect? What are the threats to those assets? And then on looking on how to implement protective measures for that and reiterate. And if we look into the automotive definitions, like in the 21434 series, we see that that standard with slightly different terms and slightly different definitions, but the general gist of it is the very same. We have an overall security management with the definition of the process and responsibilities, including the monitoring of those activities, naming audits, and regulation of those activities, also distributed. In that case, if I'm the OEM, I have to involve my tier 1, tier 2, tier 3, and so on. I need to continuously monitor anything. I need to have an incident response. That means incident response I need to monitor the market, and I need to be open to that someone is trying to inform me that there is a problem with my system, with my devices in the market, and I have the appropriate process behind to react on those information, and don't block that out, but react, look into it, and look up what needs to be updated, what needs to be modified, what needs to be improved, and then distribute those updates to my customers, to my, maybe if I'm a tier 3, to my tier 1, and then finally to the OEM. And again, here the main element is what I already said. I need to make a threat analysis and risk management, and here it is called Terra. I have to derive my security requirements, and for that I has to do verification, validation, or in general what we completely say security by design. You see, all those standards are in a very similar. It's a system definition. I have to look at my whole system. I have to look on what are the assets, what are the threats, and what I then do to protect those assets. I said already, what are assets? Assets could be software, firmware. We are in a connected world and we are doing updates. So that means my update, my firmware is maybe a protected asset that could be read out also. Especially if I want to sell as a business functionality as a service, then my software, my firmware is the asset, and I have to protect it, and I have to look on how to do that. An asset could be business-related data, and then I have to look on what is the threat model for the business-related data. Like if data could be like if I'm in a taxi, the data is being transmitted from the taxameter to the cloud, then the business data needs to be protected while the data is in transit. But the business-related data is also the taxameter. While the taxi driver has the whole day access to the taximeter, he can manipulate the data of the taximeter. So the taximeter maybe needs to be also protected from the taxi driver. Again, we have to look at the system point, what are the assets and what is the threat model. Maybe it's the running system, or maybe it's the theft of parts of the system or of the whole system, which I want to protect. Different threat models could be, is it a closed system? So I have physical restricted access. Only certain allowed people are allowed. You know that normally in IT, to the service in the cloud infrastructure, only certified and allowed personnel with with access cards are allowed in there and to work that. We could have this for embedded networks as well. Or is it an open system like in mobile machines, where the machine is sitting on the road the whole weekend or on the sidewalk, and everybody has access to the machine unmonitored? If is only local access possible, like I need to physically access the device or the system, or is remote access is possible because everything is connected like these days? And so I have to look on those, and just with a practical example, Kent Handel had last year a report on that. A friend of him had detected some problem with his car. They messed with the headlight. He wondered what happened. A few weeks after that, or some days after that, he knew his car was basically gone. It was stolen. They investigated the issue, found out they used a theft device that was obscured as a standard Bluetooth speaker, but inside it was completely modified to be connected to the CAN system, which was behind the headlight and which allowed to steal the car. And how that happened was The thing is, these modern cars, we are using remote keys and we use encryption in the keys. Encryption these days is very good and it's hard to steal, to break the encryption through the keys. But the problem is we have those networks, those embedded networks in this example here, where we have our headlight, we have the key receiver, we have a gateway, have the door control and the engine control. And what we see here is from the headlight, I was able, via this theft device, to allow the door control and through the gateway to allow engine control. And that's the problem. And can also describe a simple way to mitigate this, threat model. Yeah, the gateway just had to be reprogrammed to not let or to allow certain data from the headlight going to the engine control, because the headlight could not talk to the engine control. So what I want to say is there is an encrypted way from the smart key. Everything was encrypted. A headlight is not an important asset. Switching on and off the light is maybe safety related, but not so much security related. But the issue became that this could be used as to gain local access with physical access to the network and to issue commands, which were then accepted by the gateway and even forwarded without any protection to the engine control. So, and that's what I mean. We need to look at the whole system, look at the asset and what needs to be protected. In this case, there would be two assets. First, door control should not be open and closing, or specifically open the door should be not as easy, but also starting the engine should not be allowed without certain requirements. So, and if I identified and have done that, then I can start and can look at different measures, what I can apply. If I have my CAN model, then we have in our CAN model different protective measures which I can apply. We could apply something which I like to call the transceiver security. We have some protective measures on the data link layer, like we are currently developing CANSEC for the use in CANXL. We have a suggestion and implementation or version which is called CANcrypt or generic CAN security on the frame level. And or maybe I need a real end-to-end encryption and end-to-end security between two signals, because I don't care what's been below. I want real end-to-end encryption. And so that's something I have to look at. What are my according protective measures? Transceiver security is, yeah, there is a transceiver available, for example, which implements a block and pass list. So that means I can program into my transceiver a message filter, which allows only certain messages from the CAN bus, yeah, going through the transceiver from the MCU onto the CAN bus and vice versa. So that allows me, for example, even if that is a device, a node, which has an upper connection, like internet connection, like a gateway, and that node is being taken over from a bad guy, he will not be able to issue any CAN message into the network because that is being fixed by the manufacturer of the device in a block list and in a pass list. The trade-off, of course, is I can't use dynamic CAN IDs because that would require to reprogram block list and pass list. But if I'm allowing a reprogramming from the MCU side and the MCU is taken over, then the bad actor, of course, could reprogram those block and pass lists, and that defeats the purpose. So you see, we have some simple possibilities on the physical level, somehow physical level, by using secure transceivers. A more, I would say, improved version or better version is I would be able to detect bad actors in the network. That is a concept. It's more like a concept. It was presented on the 7th International CAN conference, like putting an oscilloscope or some other similar measuring device. And if I monitor the CAN signals, the behavior of the CAN signals, the levels, the timings, and all these kind of things, I could make a fingerprint of my clean system. And if I monitor in the running wild, I could detect if a bad actor is being connected to the network or not, and or if something changes, and then that could be signaled, and according mitigations could be started. At a very old presentation, very old CAN conference, Bosch had presented something what they called plug and secure communication for CAN. It was more also a proof of concept. They used the commonly known and well-defined Diffie-Hellman key exchange and applied it to CAN directly and used it to extract a shared secret between two nodes. And that shared secret could then be used as a symmetric key for the encryption or the authentication of data. But that was more proof of concept. A version from that was developed by EMSA as part of the original CAN system, which was called or is called Scalable CAN Security. That doesn't use CAN directly in a way that we use the arbitration mechanism of CAN to derive a shared secret, but to make that on a message level and derive transmitting messages with different identifiers and derive that from that way. It is not as fast as doing in the arbitration directly, which needs dedicated hardware support, but it allows also to make basically Diffie-Hellman key exchange on message level. If I'm going the next layer up with CAN security or CANSEC and CANXL, what we are currently defining in CANXL, here we first go on and defining what we call a secure zone. In a network, I can have one secure zone or several secure zones, and one node, like in this case, node A, can participate in one secure zone, or in this case, node A can participate in two different secure zones. And what we do is node A, in this case, and what we have in addition is what we call secure channels, SC. And in a secure channel, the data is being broadcast to different nodes. Like in this case, node A is broadcasting its data into CAN in a secure channel A, and then the data can be received by node B and D, but not node C, because node C is not part of the secure zone. And the same happens then for the secure channel of B and for the secure channel of D. So everything is being broadcast. To enable this communication, we have, from the definition point of view, we have two different levels. One level, which we call is the data plane. The data plane is defining the format, so and allows the real-time secure data exchange. So either it is authentication only or even encrypted. The data planes defines the symmetric keys to be used, the freshness values, and all the other, and the signature and all the other overhead, which is basically applied to the messages itself. Above the data plane, we have the control plane. The control plane is responsible for the configuration of the data plane and is responsible for the key agreement. So for updating the symmetric keys in the devices when the freshness value is exhausted, and or if we need a new key agreement because something was detected. So on the data plane level, that means we think about on what can be secured in the CAN frame, or specifically in the CAN XL frame. We want to secure the priority ID, the DLC, the specific data, the service data unit type, the VCI, virtual CAN ID, the address field, and of course the data field. And for that, we need a signature of some sort. And to be more detailed, the signature is then we are using an integrity check value, which requires some data depending on the algorithm used. It's normally 128 bits or 256 bits. We need additional overhead data for the freshness value, which in this case is a 32-bit value. And we need additional identification for like the secure channel identifier we are using for the secure channel, and other data and flags to identify what we are doing, like are we doing currently an authentication only, or do we do an authentication and encryption, and so on. So that means we are needing, we have defined freshness value of 32-bit, which normally runs out after 4 to 5 days, depending on the bit rates used. That means it when the freshness value runs out, we need to update the key material. We have different different modes for authentication only, and for authenticate encryption with the associated data. And we have support for different algorithms. The standard algorithm AES-GCM with 128 bits or 256 bits. And we also have support for the new and upcoming lightweight cryptos, ASCON 128, which was promoted last year and defined last year from NIST as the upcoming lightweight algorithm. Just a short comparison between AES, GCM, and ASCON. I said NIST selected ASCON as a winner about a year ago for the upcoming lightweight algorithm. What means lightweight? Lightweight means that the requirements for the lightweight algorithm requires only a factor of 0.4 compared to AES. That means if I want to implement in hardware, then lightweight means requires only 0.4 of the space in hardware than AES. If I implement both in software, then the lightweight is by a factor of 0.4 basically faster than AES. So that is the requirement, and we have defined support, optional support for both. On the control plane, we are currently in the development on the key agreement algorithm. The original idea was to use MKA from the Ethernet world, from the MACsec world. So it stands for MACsec key agreement. It has the plus to be approved mechanisms because there is implementations available. Unfortunately, it has shown it is only for peer-to-peer communication and not for multicast broadcast communication. So that means the performance for multicast and broadcast communication is poor. Just for an example, a key agreement with basically 2 nodes means it requires normally 5 seconds to update the keys. Key agreement with 6 participating nodes, we have 2 seconds was. With 6 nodes, we require 64 seconds to have an updated key between all devices. You see, for embedded systems with real-time requirements, where on the fly I need to update my key material, 64 seconds is a lot of time. So we are currently in the in the development on the decision on how to either modify MKA, how to improve MKA to be used for broadcast communication, or is it to define a new optimized version of that for for multicast broadcast communication. As I said, it is in development, and there are no final decisions being made. Parallel, we have a proposal and first work draft of a generic CAN security solution, which is more intended for CAN FD and CAN CC, or classical CAN. Here we use again the same. We need to identify the data that needs to be protected, and then we add a signature to that. And the signature is then could be mapped to, in this case, for example, to CAN-FD. And the signature is could be then consists of a 32-bit part for information, like identification on what algorithms, what keys, again, all those additional meta information which is required. Also here a freshness counter and information that I always require to secure my communication. And then, of course, the signature itself, in this case, for example, a 32-bit value. Or if I want to map that to classical CAN or CAN CC, then I have to look on, in the example before, for mapping on CAN FD, we needed 64 bits, so 8 bytes. That would imply the whole CAN message. We wouldn't have any space for data. So one suggestion is, for example, to use the extended, the additional 18 bits of the additional identifier and truncate all the data in here. But of course, as you know, if I strip down on the data, it always weakens security. And that's, again, coming back to the original question. I have defined my assets. I have identified my my threats. I have thought about the countermeasure. I now have to think, is this enough to secure my assets in a certain way? Or if it doesn't fulfill my requirements? And of course, it depends on what I want to achieve with all this. Here we have also a defined key agreement algorithm, which consists of different roles in the system and several messages which needs to be exchanged. But the general rule and general definitions and format is the same. And then finally, I want to give a dedicated example for the application security, so for real end-to-end security, and that is, for example, the ISO 16844, the tachograph definition that is in use in any truck these days to monitor the truck driver. because the important asset is here recording the speed of the truck and also at how many hours the truck is driven. And the threat model is the truck driver wants to mess with the data because he wants to drive faster. He wants to drive longer hours. So here it is defined. I have my motion sensor that is normally physically attached in the gear of the truck. And I have my recording equipment with card reader, display unit, printer, and so on, which is normally physically installed in the driver cabin. And then I have my CAN communication between. Here is also a secure CAN protocol in place with a temporary key distribution. The keys are only held in RAM. So if the system is being powered down, the keys from the RAM are lost, and as we initialized in a certified service station. In addition, it is physically secured with a tamper-proof cable, and it is just to have an end-to-end protection of the speed signal, basically. And of course, I said you need to also think about, which is not really specifically for the embedded part, but for the general part, about incident management. Incident management is, as you know, maybe from IT industry, is someone detects a problem or a bug or a general structural problem with your implementation and wants to inform you, then you need to communicate what is the process to for the general public, for researchers, on what's the process on how to inform you, how to give feedback, because those people who informs you want to have feedback on what happened with their reports. And most of the time, researchers aren't doing it for free. Their payment basically is they want to publish their research at some point in time at some security conference, and at that point you should have fixed your problem. With that, I want to basically close my webinar, and like with any of my presentations, there is a case study for everything. So the best security doesn't help for anything. There's always a way around your security, and you need to think about. And with that, I want to close and like to thank you. If you have any questions, please feel free to ask them in the chat, and I will try to answer them. And if you don't have any question, thanks for staying with me, and maybe seeing you at some next conference event.